Alright, today we're going to be going over spanning a vector space. So first, let's define what it means for a set of vectors to span a vector space. So what this means is that every vector in that space can be expressed as a linear combination of the set. So for example, if we have our v1 here and our v2, our v1 being 1 and 0 and our v2 being 0 and 1, meaning that they are the standard basis for vectors for r squared. So let's say we have a vector of a and b, which can be written as a linear combination of v1 and v2, which would give us our a and b equaling to a of v1, which is going to be 1 and 0, plus b multiplied by our v2, which is 0 and 1. Since we can represent our answer here in our R2 space, then this and they're going to be linear combinations of each other, as they will just become a0 plus 0b, then this will span our vector space. Alright, now we're going to go over our vectors in our 3D space. So we have our u1 of 1, 0, 0, our u2 of 0, 1, 0, and our u3 of 0, 0, 1. Which make up the standard basis for vectors in R3. Now, the way to find if a vector spans in R3, what we need to do is we have to write it as a linear combination of a new vector, which for this case will be x, y, and z. So to tell if a vector spans is it will become a linear combination of all our basis vectors. So for x, it will be x, 1, 0, 0, plus y, 0, 1, 0, plus z of 0, 0, 1. Now, if this becomes a linear combination, meaning that it is a scalar multiple of our original condition, for this case it's our standard basis for vectors, then we will know that it spans in R3. Since we're able to write any vector as a combination of our x, y, and z multiplied by our standard basis, this means that it will span our R3, as this will just become x, y, z are all real numbers, meaning that this will just be any linear combination of our standard basis, meaning that it spans R3. Alright, so we have our first example, which is asking, can vectors w1 and w2 span R3? So our w1 is 1, 1, and 0, and our w2 is 0, 1, and 1. So what we want to do is we want to have a vector that is a, b, and c, and we want to see if it's a linear combination of w1 and w2, which would mean that it does span R3. So what would happen is our a, b, and c is going to be equal to x of 1, 1, and 0 plus y of 0, 1, 1, which gives us x, 0 plus 0, y, which will give us x plus y, and then y when we add across, because we're going to add our first element plus our first element, our second element plus our second element, and then our third element plus our third element, which will give us this vector at the end of x plus y, and y. Now we're going to match this up with our original vector of a, b, and c. So as we can see, a will be x because they're both our first elements, b will be x plus y, and c will be y. Now this means that for any vector of a, b, and c to be represented as a linear combination of w1 and w2, the condition of b is equal to a plus c has to be true, because a is equal to x, so we can replace the x with a, and we can replace the y with c, as c is equal to y. Since not all vectors in R3 can be represented this way, we know that w1 and w2 do not span R3. Now, we know this isn't true because if we have our a, b, and c our A, B, and C are all random numbers. So we could have an instance, I'll write in red, where our A could be 1, our C could be 1, but our B also could be 1. But our B being 1 does not match with our A plus C, meaning that it will not span our R3. Alright, and now before we go into our second example, we're going to go over the steps to determine if a set of vectors spans the vector space. Our first step is going to be taking the vectors and form a matrix with the vectors as columns. So if we had a vector of x, y, and z, and that's going to be 2x, 3y, and 3z, for example, we'd put it into a matrix of 1, 1, 1, and then 2, 3, and 3. Next step is going to be putting it into row echelon form, meaning that we want to have the form of 1, 0, 0, 0, 1, 0, and 0, 0, 1, or the best we can. We might have some free variables, but that's okay. We want to just try to get it to as close to this form as possible. And then finally, we want to check the rank of the matrix. If the rank equals the dimension of the vector space, the vectors span the space. Alright, so what we're going to do is our first step of putting all our vectors into a matrix. We're going to have 1, 2, 3, 4, 5, 6, and 7, 8, 9. Now we're going to try to have it as close as we can to our form of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So our first step is we're going to subtract 4 times row 1 from our second row. So it's going to be R2 minus 4R1, which will give us 1, 2, 3, as that doesn't change. And this will give us 0, negative 3, and negative 6. And then our last row doesn't change. Then, next step, we're going to subtract our third row by 7 times our first row. So it'll be R3 minus 7R1, because we're going to try to clear out our first column, which will give us 1, 0, 0 for our first column, and now this will be 2, 3, negative 6, and then negative 6, negative 12. Now we're going to divide our second row by negative 3. So we're going to have R2 divided by negative 3, which will give us 1, 2, 3, 0, 1, and 2, and our last row doesn't change as 0, negative 6, and negative 12. Then what we're going to have is we're going to have our first row minus 2 times our second row. So R1 minus 2R, which will give us 1, 0, negative 1, 0, 1, 2, and 0, negative 6, negative 12. And now finally, to clear up the last row, we're going to add row 2 multiplied by 6 to row 3. So it'll be R3 plus 6R2, which will give us a final answer of 1, 0, negative 1, 0, 1, 2, and 0, 0, 0. Now that we have it in the row echelon form of the matrix, and it shows that there is 2 non-zero rows, which are going to be our first row and our second row, because they're not all zeros. This means that our rank of the matrix is only 2. And since the dimension of the matrix we're looking for is R3, and our dimension we're looking for was 3, and since our rank of 2 is less than the dimension, it means that our vectors of v1, v2, and v3 do not span R3.